Okay, so we're looking at the next lesson, which covers translations. This is section 4.2. So our learning goal for this lesson is that students will understand, use, and construct translations of plane figures. So our different success criteria are below here. We want to be able to identify a transformation that is a translation. We want to be able to use ordered pair notation to represent a translation on the coordinate plane. We want to be able to use a translation matrix to represent a translation. And we'll talk about this one particularly in class, not in the video. And then we want to be able to construct a translation of a figure on the coordinate plane. So let's begin. Okay, when we look at something that slides, any kind of sliding motion, is called a translation. So we're not going to rotate it, we're not going to flip it, we're just going to slide something from one location to another location. And when we do that, we call that a translation. Some of the properties of a translation are that a translation is an isometry. And remember, an isometry means that the figure doesn't change its size or its shape. But another property of a translation is that it doesn't change the orientation. So if we look at the points in alphabetical order on the pre-image, and if they go clockwise, then in the image they're also going to go clockwise. And so I think I've already got them uncovered here, but you should put these questions in. What are the properties of a translation? And why is a translation an isometry? Because it doesn't change its size or its shape. Okay, next. One of the ways that we can describe a translation is using vector notation, or by expressing the translation using a vector, I should say. So for example, in this diagram here, we've got this vector right here, and we call the vector A prime. Now this notation is the notation that we use to describe a vector. The first point is the beginning point, and the second point tells me the direction to go. And we use this little arrow. It's kind of a half arrow. It just has one little half of the arrowhead at the top. That's how we write a vector. And it tells me how to move the figure, right? So if I'm looking at point A as my starting point here, get a little red pen here. If point A is my starting point and point A prime is my ending point, my vector has two components, right? It has an x component and it has a y component. The x component says move it over 2 units to the right and move it over, move it up 1 unit in the vertical direction, move it up 1. So if I wanted to translate this figure using that vector, I would look at the vertices of my figure. So I'm going to take this point here and I'm going to move it 2 units to the right and 1 unit up. So now it's going to be here. I'm going to take this point, move it 2 units to the right and 1 unit up. And then we'll do the same with the bottom. Take this point and we'll move it 2 units to the right, 1 unit up, and the last corner 2 units to the right and 1 unit up. So using a vector just kind of gives you an idea of how far to move a figure and in what direction, but it doesn't give us any quantifiable measures. It doesn't say move it 3 units or 4 units. You just have to look at the vector to determine how far to move it. Okay, so our question we could put over here, how do you use a vector to represent a translation? Okay, so another way we can represent a vector is using ordered pair notation. And when we're talking about a vector, notice how my ordered pair here is not in parentheses, but it's in these kind of pointy brackets. These pointy brackets tell me that this is representing a vector instead of an ordered pair. Now a vector is different. An ordered pair is just a point, right? But a vector is telling me move. Move this thing and move it in this direction. So vector tells me direction and distance. So let's look at this particular example. The first number that we see here, the 5, tells me how far to move my figure in the x direction. And then the second number, -2, tells me how far to move my figure in the y direction. So here in the diagram, we have point A, and then we have point A prime. And you can kind of see point A moved 5 units to the right in the positive x direction, and then it moved 2 units down in the negative y direction, and that's how I got to my new location of A prime. So I've translated the point A by the vector 5, -2. So this is a good question. What notation do you use to represent a vector? And the notation that we use is this little piece right here. Okay, let's do another example. What is the image of P under the translation 0, 4? So what I'm going to do is I'm going to take point P, and get a different color here, we'll use blue. Here's point P, and I want to move it 0 units in the x direction, and I want to move it -4 units in the y direction. And so if I did that, if I start at P and I move 0 units in the x direction and 4 units down, you can see that I'm ending at Q. So to answer this question, I would say that the image of P under the translation 0, -4 is the point Q. All right, the next question asks, what vector describes the translation that moves point S to point U? All right, so if I started at S here and I move to point U, we need to figure out two things. We need to figure out how far did I move in the x direction and how far did I move in the y direction. So we'll kind of draw those two components right here. And I think you can see that in the x direction we moved 3 units, but we moved 3 units to the left. So we might write -3, and then we moved 1, 2, 3, 4, 5, 6 units down, -6. So that would be my answer here. And I don't have the right symbols to make those look right, but we would use that vector notation, -3, -6. Okay, so one more example here, and this is working with a translation with a slightly different form of notation. And this asks me to translate the triangle RSP, which isn't there yet, we'll have to draw it, using the rule xy maps to x + 2, y - 4. So that's telling me that every ordered pair is in my pre-image. I'm going to add 2 units to the x-coordinate, and I'm going to subtract 4 units from the y-coordinate. So let's start by drawing our triangle RSP. So these would be the sides of that triangle. But to translate it using that rule, I just need to take every single point, move it 2 units to the right and 4 units down. So let's take point R, move it 2 units to the right and 4 units down. Now, so here would be my new R, and let's go ahead and label that. We maybe need a smaller thing here. R prime. Let's see if this is smaller. R prime. Perfect. And then we want to take point S, and we want to move point S 2 units to the right and 4 units down. And I'm labeling these points because there's a lot of other points in my diagram here, and I want to make sure that I remember which one is which. So this is S prime. And one more we got to do. We got to take point P, move it 2 units to the right, and 1, 2, 3, 4 units down. And I'm going to move this label so it's over here, and we're going to call that P prime. Perfect. Now all we have to do is connect the dots, and we have our transformed triangle. It happens to be on top of a couple points, but I know that it looks right because its size is the same, and I know that a translation is an isometry. And if you wanted to, you could make the statement that triangle R prime, let's get my little triangle here. We can make the statement triangle R prime S prime P prime has coordinates R prime would be at the coordinate 1, negative 2. S prime would be at the coordinate 4, negative 1. And P prime has the coordinate 5, negative 2. And that's great because we could take the coordinates from the original triangle, add 2 to every x, subtract 4 from every y, and we could get the same coordinates of our translation. Okay, so that's all I want to do in the notes today. For tonight, we'll talk about translation matrix in class on Monday, so be prepared for that. So go ahead and make sure you put in your questions on the left. Put the example questions on the left-hand column and go ahead and write your summary.